Hello, my name is Peter Dell. I'm working for SAP for many years, almost 10 now. My talk is about what I call the opposite of HANA. It's the Atari Video Computer System. It was called Video Computer System 2600, also known as Stella or VCS. The slides that I present here are partly based on a talk that a colleague of mine gave at the Chaos Computer Club. And I try to strip down as much as possible, so some information is kept in, and I can still give you in the second part of the presentation live coding, a bit of live coding to show you what coding looks like and how the code looks like that you create on that machine. Okay, so this is about programming the Atari 2600. There's one here that's currently running, up and running. There's a game cartridge in, which has 4K. This is how a typical game cartridge looks like. There are 4K of ROM on it. I can hand it out so you can have a look. And maybe I start with a bit of history and my personal background, which perfectly fits to the Moore's Law. So my first computer was a ZX81. I sold it together in 1984. It had 1K of RAM. 1K of RAM split into two chips of 512 bytes each. And I got the layout here, so with a CPU and the ROM and the RAM and the rest, which is one chip. And the TV got later, which is the most important thing because you had no monitor. It was a home computer, so you could connect it to your TV. So I will also hand that out. Please do not touch the chips directly with your fingers because they are sensitive to electric statics. Yeah, time went on. My ZX81 actually broke and I had to get a new computer, and it was an Atari 800 XL. This is why I'm wearing this shirt. It's my favorite machine until today. And it had 64K, which was amazing. It was as much as the C64, which came out at the same time. And I went on and I got an Amiga 500 5 years later, which had now 512K. And this goes on with an Amiga 1200 with 2 megabytes, and my first PC in 5 with 8 megabytes of RAM. And then, in 2009, I got a book. A friend of mine gave me this book as a present for my birthday, and it's called Racing the Beam. This is a book from MIT Press, created by people who analyzed computer architectures of the past and why they were unique. And this is a very unique system in many respects, and I really recommend, if you want to know more about this machine, to read this book. It's very easy to read if you have some understanding. If you remember how this game looks like, you will find it again in the technical details why it is like that. Okay, so I got this book and I thought, hey, that's not so difficult. It's basically my Atari XL and some chips are missing. So let's go there and code something for it. It must be possible. That was my first thought, and then it was a very, very misleading thought. So I got my VCS in 2010, my first one, and it had 128 bytes of RAM. Yeah, so everybody says, ooh, of course there's also RAM. There's not only RAM. Yeah, you need RAM to do something with the CPU, but ROM is also important. So there are 4K of ROM. Yeah, so if you need program or graphics, you do not have to load them into RAM. You need the RAM to store your game position, the level, the name of the player, the computer stack, the CPU stack. It's also there. You have to fit it in. Yeah, so when you go to a subroutine, for example. And yeah, when you compare this to today, where I'm working at HANA XS actually now at the moment, and we have HANA installations with about 100 terabytes of RAM. I went to Wikipedia and I tried to find a word, I couldn't. And in the end it is 1 million by 1 billion times as much RAM in that HANA box as in this machine. So it's absolutely, you cannot compare these two. And this brings us to the question, what actually is it and how the hell could it work? Okay, it is an Atari machine. Many of you know the term. Atari is a company that was founded in the year I was born by Nolan Bushnell and Ted Dabney. And they were into game machines, and these game machines were actually arcade machines that meant boxes like this that you maybe know from your youth or from a casino. And yeah. Big boxes, discrete logic, every game was soldered together in hardware with discrete chips, or sometimes even special chips that they created. And the game screen looks like this, and if you now look here, you will see some similarities already. Yeah, because Pong Arcade was a huge success. Atari made lots of money with it. There's even an anecdote that says that the first pub, they called it after a week and said, machine is broken, and it turned out there were so many coins in. Yeah. So what did they try to do? They first did a home version of that hardware Pong, yeah, with pedals, and they sold it, and it also was a big success. And because Nolan Bushnell was a businessman, he said he wanted more money. So how can we make more money of it? And the engineer said, well, it's very expensive for every game to design a new hardware. Couldn't we somehow separate the game logic from the hardware a bit? And he said, well, no. So they started, why not? And they started a project codenamed Stella, and that's also the codename for that machine, for somehow programmable design that could do the same as this arcade machine, or similar things. Yeah? And it was not intended to be high-class, super technology architecture or something. It was meant to do the same with less money. And that's also the goal. The primary goal of this whole design was not to be good. It was to sell in a short time frame as many units as possible and make money out of it. And many design decisions point to that. So what costs money? First, when you look at this PCB board that I gave around, it's CPU, the I/O for the controllers, the TV connector, and the RAM. That is what you need in the console. And what they decided is, we do not put any ROM in there. ROM we put on these cartridges. Cartridges are cheap to produce, it's mass production, pressing 100 at a time with a partly mechanic process. That's not much. We can sell them for, let's say, $50. And that was the second decision by Nolan Bushnell. So something that was worth $5 in hardware, he sold it for $50. And this is why Atari made so much money with it. And they put everything on a cartridge and multiple cartridges per console. They had a cost limit. $200 must not be exceeded because it was intended for people to buy it and use it at home. And nobody would have spent more money than this for something he has at home. And therefore, the primary design principle of the console was to save money. And to save the cost of production. And side note, how successful was this thing that where he wanted to make much money fast? In the end, this console was produced in a period of 15 years. It went out of production in 1992 with, at that point in time, 30 million units sold. As a comparison, the Xbox sold 24 million. Yeah, this was even more successful than the Xbox over the years. There were multiple designs also over the years. The first design was very large and had 6 switches and a wooden design. And this is the classic Atari joystick controller that you see here, the square controller. It's also said that Atari invented that kind of controller. And like also they said, these home game machines, or games at all, they didn't call it a game or a console, they called it an Atari, because it was the only one that was there. And as time went on, they created different designs. It became smaller, even more cost-effective. This one that you see here is the Darth Vader console. That's a code name for it because it's black. And you see, the switches have gone closer together, some are on the back. The design has become cheaper again. And yet cheaper, some years later, Moore's law, everything was better integrated. They could produce cheaper chips. And there was a junior console, 6 years after the initial release. And I also have it here. And I hand it out. Also here you will find what you see later in the block diagram. There's the CPU, there's the I/O and RAM, there's the television, digital adapter, and the modulator for the TV, and this is the cartridge slot. By the way, I would like to have them back. Okay, so this hardware that I showed you on the PCB, so what does it logically look like? The Atari is consider it a black box. So what is connected to the Atari? You see everything here. On the one hand, there is this ROM module that I showed you, where all the game is in, the code, the graphics, and everything else that you could deliver as a game. Then there are input devices, this joystick that you have seen. There are other types of input devices that are basically variants of joysticks. If you don't know the term, I have no pictures here, it's not that important. Important maybe is there's also an analog controller called a pedal. Then you could actually connect 4 pedals to one machine. Yeah? And also, like in this arcade game, this machine has not the capability for any artificial intelligence. Yeah? And therefore, they always try to make multiplayer games that could be played simultaneously, so they could save that ROM and save that code and let the game people play against each other, even if they were four at the same time. Okay, output device, there's only the television for video and sound. Within the Atari, you have a 6507 CPU, which is basically a 6502 CPU with less cost. Then there is a Riot chip. Riot is a short form for RAM, I/O, and timer. These are the three functions provided by the single chip. And this is one reason why they bought this chip, because RAM was already in there. They didn't need a separate chip. And the TIA, which is the only Atari-specific chip in there. They invented it on a breadboard. Yeah, this is where you have lots of holes and cables, and you put in a resistor, and you try it out, and they designed it on a breadboard. And it was also designed to save money, therefore it has basically no transistors inside, or only few. And this has the output for the video and 2 voices of audio, and it provides the conversion of the controller signals to something like a position. Okay, so what were the design decisions? The CPU and the chipset were off-the-shelf components, which only cost $12. Yeah, they had different offers at the same time from Intel and Motorola, and the same thing from Intel and Motorola would have cost $100 to $200. The 6507 CPU is the same CPU, is the same instructions, everything's the same, but to put it in a smaller die, in a smaller chip, they left out some lines. They said, oh, we don't need IRQs, we don't need interrupts, and what about the 64K? Nobody will ever need 64K, so let's leave these address lines out. We don't need so much. Yeah, and so we can have it a smaller chip, which is cheaper. And the full address space of this chip is only 8K. Then we have this I/O chip, the Riot chip, which was used because anyway you need an I/O chip, because the joysticks, they must connect somewhere in the address space, and this chip already had the RAM on board, so you don't need a separate chip. And we have no ROM, no operating system, nothing in the console, because everything is anywhere in the cartridge. And now when it comes to this RAM, what is the most important factor for RAM? When you create a TV screen, like you do it today, you have your graphics card or something. Back in the days, it would have meant that for every pixel you need a byte of RAM, and for a normal TV, it would have meant 32K. Apart from the fact that this nobody could have paid, that would have been in thousands of dollars, the CPU anyway could not address it. And the decision was, yeah, we don't need any additional chip create a video signal. Yeah, all we have is we have the CPU, and it's the CPU basically driving the beam on the screen. Yeah, so while the beam travels, the CPU produces the output. Every single pixel with a little help from this video chip, and this video chip has now very unique names, but if you remember this Pong, or you see this game, I can very easily explain what this chip was capable of doing. So this chip produces one line on the TV, one scan line at a time. Yeah, if the CPU doesn't do anything, this line is repeated down the screen until the CPU tells the TV to now start a new frame. Yeah, that means within this black area, the CPU simply waits. In this area, it starts writing some data into the so-called play field. The play field is the static part of the screen, which gives you 40 pixels per line. Yeah? I don't tell anything about the vertical resolution, because there is no such thing as a vertical resolution. Yeah? It changes when the CPU writes there. If it doesn't, it remains. So these 40 pixels, again, they would mean 5 bytes. But since the CPU needs time now to write this data into the chip with every line, they had to make a decision, and they found out that if I change 5 bytes for this screen line with every line, then the CPU has no time left to do something else before the next line starts. So you would only see some playfield. So they said, we don't need 40 different pixels, let's only put in 20 different pixels and 1 bit to tell the video chip if this is to be repeated or mirrored. Yeah, and this is the reason why if you say the video RAM of this thing is 21 bits. Okay, then we have one more bit available which can move. This is the ball. Imagine why this sprite is called the ball. And other systems call it sprite. So now we have the movable objects. They can move at a, you can see it, they can move at a more fine granular positioning, but it's just a single pixel. You can change the size, but it's a single pixel that you can control. And then we have the players. This is what they are called, these two sprites called players, and as you can see they can have individual colors. These players are 8 pixels wide, and again there's one more bit to save memory on the chip, and with this one bit you can make the sprite flip. It means if I go here and the sprite turns over, it doesn't mean we have 2 graphics in the ROM. Yeah, we have only one graphic, and the CPU can set a bit to say, let's mirror the player. We save 20 bytes. Okay, and then there's one more thing that you cannot see here. You can see it, it's the missile, and this missile is again one single pixel that you can control in the color of the player, and if you look closely you can see what the missile was used for. Yeah, these thin lines here are much more than these 40 pixel resolution. Yeah, so obviously they are not the play field. Yeah, this is 1 pixel and it's moved every line a bit wider to the left, and here it's moved to the right. And it has the same color as the corresponding play. So this screen contains everything there is to create graphics on this machine. Yeah, and if you have a game idea, you have to fit it somehow in there. Okay, here are more examples of games. This is a basketball game. Then there is Hangman, and you see, okay, this is a play field, and up there are player 1 and player 2. This is a soccer game. You see the player 1, 1, 2, 3. Now, always imagine the screen is built top down. Yeah? So what does it mean? It means this is player 1, this is player 1. Yeah? It's just switched on and off, and the position is changed, but it's the same player. For the CPU, there's only a single line at a time. And again, this is player 2, and this is also player 2. This uses a feature also from the video chip. Like for the playfield, the CPU would not have been fast enough to update more player graphics per line. So what they did is they added 3 more bits, so you can say, oh, this player, please repeat it again in 16 pixels. And there's also a mode to display it 3 times. And when you see different games, you have, like for example, in the first level there's only 1 enemy. In the second level there are 2 enemies, and in the third level there are 3 enemies. And actually it's the same sprite, it's the same code, just the video chip is told to display it 3 times. And what you can see down here is that as time goes by, so this was 6 years later, people got more knowledge and experience with this machine. So limited it is, so flexible it is, because the CPU can do everything at any time. Yeah, and you can start playing around with the timing. When do you change what? And create more effects. Yeah, so instead of simple stuff here, they really put in animated players, because they had learned how to do this in the code. Okay, some more examples. Pitfall, maybe one of the most famous one for Activision, which was an excellent game company, and this is one of the last game cartridges, Solaris, which is a game, if you play it through, it takes hours to really complete. And these 2 things below, these were my tries to do something on that machine. As you can see, they're extremely colorful. This is what this machine can do. Yeah, so you only have 4 color registers for background, foreground, player 1, player 2. But the palette is immense. It has 128 colors you can choose from. And maybe you see it also in this attract mode, so it starts changing the colors. Yeah? It doesn't mean there's more RAM or something, it just changes the color value. So there are many color values, but only 4 colors to choose from at a time. Yeah. Okay. Last thing on my slides, before I start with the coding part. How is this display created on the TV? And you can also see it on the TV. TV, from technical point of view, starts with a blank area, which is called the vertical blank. Then there is the display area, and then there is the overscan area. It is you can count it in cycles, or in milliseconds. And on this machine, you typically call it in color clocks, which is 1 pixel. And then on the you have a vertical synchronization and a horizontal synchronization. That means there is a certain area or time where the TV beam is retracing, so the CPU, what the CPU does is not visible, and then the visible area starts. This is what you really see, this green box is what you really see on that TV, and everything that's black is where the CPU can do something. Yeah, like for example, compute the input or the values for the next line for the display. Okay, that was the presentation part, and now I go to the coding part to show you how you could actually code for this. What you see on the screen is an IDE that I have created based on Eclipse. It's a plugin that you can download from my website, and it provides like you use it, you know it from Java, syntax highlighting, forward navigation, and an outline of the code of the assembler code. So, what can we do here? We have some source code. It starts with an origin statement that says where in the address space shall this code be located, and we have 4K available. This is everything hexadecimal. And I start with a procedure that is called cart. There's some initialization that clears the the video chip and the 128 bytes of RAM, which are located from 0 to FF in the address space. So everything is now black, everything is 0, and we can put the stack pointer for the CPU. So if you make a jump subroutine, you need some stack. You can point the stack pointer to the upper memory, which is 127. Okay, then we have a main routine. We have this, which is the main loop. Then we have this vertical blank that I showed you. And you remember these three areas, a vertical blank. So this is the upper blank area. Then we have the playfield area that you can see. We have the overscan area on the bottom. And then we have a jump to the loop. Yeah, that means opposite to anything you know about programming, the whole program was an endless loop. Yeah, so there is no interrupt or waiting for something. You program a loop. Like the TV set generates this picture in a loop, your program is in a loop. And the important thing is, you have to keep it in sync. Yeah, so the TV beam travels down the screen, and at the same time the CPU produces a signal, and you have to keep these two in sync. That means when you create something, you have to really count the cycles that every instruction needs, because if you do it too late, the image will shift. Yeah, and if you create too many or too few lines, the TV picture will start rolling. Yeah? Of course, you have some things that do not take constant time. And for this, you have a timer that you can set. Here can I write 65 to a certain memory address location, and then this riot chip starts counting down. So I can, because I know how much time I have in that blank area, I can at the start of a blank area say, start countdown, do something like read a joystick, and then in the end, wait until the countdown is over. Yeah, and then I can jump up again. And when I jump up again, I have to set some bits on the video chip to make sure the TV gets the synchronization. So the CPU has to tell the TV, now this one frame is over, please start again on the upper left corner. Okay, so I don't care about now this whole timing stuff around. Let's focus on what you do as a game designer. You mainly think, how can I display the graphics? How do I get something that is not black in the play field? And I uncomment some of this code. Oh, that's not uncommenting. Okay, what I can do now I have to switch the cartridge. To develop code, you can either use this one, which has an SD card where you can put the ROMs in and offers a menu from which you can choose. So on this SD card, more than anything that will ever exist for the VCS, of course, fits. And then there is a similar module which you can connect directly via USB, and you can put these 4K, these immense 4K of data through this cable into a ROM emulator that behaves at runtime like the actual machine. Okay, so you have to be careful to plug it in the right way. So this is why this event is called plugin, by the way. Okay, and this is actually what this code is about. Yeah, so you see this green line, forget about the green line, but you see there are alternating lines. Some are black and some are gray. So how is this image created? We have a line counter, which is x. Load x with 0. Then we have an instruction that says store wait synchronization. And this instruction will stop the CPU until the video chip tells the CPU the next line has started. This is the most important feature of the VCS. The video chip can stop the CPU. Many other home computers did not have that feature, and when they tried to do the same, so changing colors per line, they flickered all the time because its timing was not there. Here it is built in. Okay, then I say, let's I have the wrong example. Let's load 0. Let's set A to 0. Load A with 0, and this would be store A to color background. Yeah, so here I put black into the background. I increment x. X is x plus 1, and I compare x with 192. That's the number of lines on the screen. If I'm not at the end of the loop, I branch, if not equal, to this label. Yeah, so this is a simple loop. X is counting up from 0 to 191, and with every line I can do something. Yeah, since you already see that this on the screen, I change this now. With every line, I store now the line counter. And what I can do is I can say compile and run. It takes a while because of this protocol. Okay, it did manage to get it over. So this is exactly what happens. With every line, I write the value of the line counter to the background color register. And now you see, what have we done by now? This code, by now, it requires exactly 99 bytes. That is the amount of code in the ROM, and by now it does not actually require any RAM. Okay, so I have prepared some more examples. So what can I do? I can paste this in. That's the example that I originally had. I can also do this here in the emulator. Yeah, so typically I do not have this set up at home if I code something, so I can use an emulator and at the same time run it here. What I can do now, I told you, is everything about timing. That means after I waited to start after the CPU has been waiting to start a new line, it does something like writing the color register. Now I waste some time with knobs, with no operation, and as I wait, the TV beam travels to the right. So if I again change now the value of the background register, okay, this time it worked. No, it didn't. So. You see, I always have to power it on. No, it doesn't work. On or off. Maybe I'll check it in the emulator. No, it looks the same.
Maybe because your binary file is still open?
No. If the emulator shows the same effect, then maybe this timing is not put in 20.
Are you editing the right file?
I'm also wondering. No, yes I am, but I have not included it. Okay, so to keep the code separated, I made it include, so I can code in the include, and now it will work. So you're not bothered watching the whole main program. No. This is how it crashes. And this is what I wanted to show. Yeah, so now I've waited some more time, then I change the background color again, and I change it back, and I change it again. Yeah, so you can create new effects by waiting that some time has passed and the TV beam traveled to the right. Okay, next is display field graphics. How can I create graphic graphics? Graphic graphics means that with every line I can write a value to these 22 bits that I have. Yeah, the code is quite simple, so it's just line counting, and here I have, you get from an array, I get now graphics data, and store it, and then again it's the loop. It's very simple loop, and what we get is, we get plugin. Wow.
Magic.
And then let's come to the magic and to the specifics of this console. I can now change a bit in the control register, and if I do this and show it here, you can spot the difference. Yeah. Because I did not add additional RAM, I have to decide whether the playfield is mirrored or not. I only have these 20 pixels, and then I can decide what happens. Okay, we had this playfield, so almost the last thing, these player graphics. So these high resolution graphics, where we have in total 19 pixels. We can use that. And do the same as I do for the playfield graphics. So this is what happens because the ROM is changing while the code is running. So there's no way of stopping the CPU. So it's running all the time and at the same time poking in different code. And this is what it ends up with. Yeah. Maybe for those who cannot see it on the screen, I also started here. Yeah. So if every line I poke in the same data that I poked into the background, into display field graphics, but this is a high resolution object and I do it every line, not every fourth line, and this is why it looks like this. And what you also can see here, this is this effect of setting these control bits to repeat the player, and there are certain combinations. There's not everything is possible. In total there are, I think, 7 valid combinations. Yeah, you can have it doubled in width, you can have it 2 times wide. Yeah, so all these combinations are those that exist. And you can use this to combine number of players, or if you have 3 players and one is shot, yeah, then you switch this, you do not erase it or something, and you just say it's a different repeat mode. Okay, and last but not least, these were the graphics. And last but not least, you can combine all of this into one. So I have now here the combination, the playfield graphics and the player, and I can change the combination how the player looks like. Now I need to turn up the volume. If this is needed. This is why it's not called a music chip, it's called a sound chip. Okay, so famous last words. My favorite quote when it comes to programming, there is the original documentation that Atari released for programmers in 1979. And the favorite quote for me is, the PIA has 128 bytes of RAM located in the stellar memory map from 80 to FF. The microprocessor stack is normally located down from FF down, and the variables up from 80. Hoping the two never meet. And actually that's the first thing I went into. So, there is a free IDE, you can find it on my website, it runs on Linux and Mac and everything, emulators included, and if you have questions, feel free to contact me, I'm happy to help.